So let's get started with project phase 2 demonstration. The deliverables for this phase of the project was to design a multi-core, multi-threaded processor and integrate it with the hardware pattern matcher, right? So we were able to achieve those. In order to do that, we have designed two separate blocks. One is IDS.v and the other one is master.v that goes into the reference router pipeline. So when the packet comes, what IDS.v does is it takes the packet and it examines for a pattern. So that pattern can be given through software register to the hardware pattern matcher in the IDS.v. And if there is a pattern, it indicates it using a flag, the presence of the packet using a flag, right? And that flag is sent along with the packet to the next block, that is master.v. So there, when the packet and its flag comes into the master.v, it is routed into one of the cores, depending on whichever core is free at that time. And then what basically the network processor, it does some kind of processing on the packet. So depending on the pattern, presence of the pattern, it does one kind of processing, and if there is no pattern, it does another kind of processing, right? So that is taken care, and all of that. So both the processors, both the cores will be simultaneously running. So since it's a multi-core design, and then when they are done, actually the packet is let go. Right, so let's look at a demonstration of how it works. So you can see the packet is coming now from the pipeline, NetFPGA reference router pipeline. It goes into the small 5-phone hardware pattern matcher. Now the pattern matcher is working, and it sees that the packet is safe. It doesn't contain the pattern we are looking for. Now the packet is let go, right? So the flag is set to 0 now. Now that packet comes to the master.v pipeline. So there is something called dispatch unit. I'm going to explain that further how it works. So that dispatch unit is going to route it to one of the cores, either core 1 or core 2, whichever is free. Right, so now it's going to core 1. Also, at the same time, you can see another packet has arrived in the hardware pattern matcher, right? So it recognizes that this packet is bad, that is, it contains the pattern. It doesn't right away drop the packet. It indicates, it sets the flag to 1, and then it sends, right, to the master.v. Now you can see the first packet, which was good, now goes into core 1. It is undergoing some kind of processing, right? Now the packet 2 has arrived. Since core 1 is busy, now the dispatch unit is going to route the bad packet into core 2 now. See, now the bad packet is in 542, that is near core 2, which is a data cache for core 2. Now the good packet is done processing, so it is let go, right? So it goes back into the intended destination. Now the bad packet is being processed by core 2, so it's gonna do different kind of processing, routed. So what we are doing is we are changing the IP address, the UDP ports and stuff. So that will be routed to our internal system, right? Whereas the good packet will go to its original destination. So that went, and the bad packet goes into the whatever the changed IP address, that is our internal system for further examination, right? Now let's look at how these dispatch and issue units work, right? So basically the dispatch unit, I have designed the an FSM that follows something like this. So what this synthesizes is basically two muxes near core 1 and core 2. So whenever there is let's say core 1 is free, that indicates by saying in underscore ready of core 0 or core 1, that is high. And when core 2 is free, that also indicates by setting in underscore ready to 1. So based on that, we are giving the control of the packet and the in underscore data, whatever the interfaces to the previous module that we are giving, that will be routed to one particular FSM. So that is explained in this diagram. So as the packet comes, whichever core is ready, it will be routed to that. But if none of the core is ready, in underscore ready for the previous block, the above block will still be 0. So no packet will be coming in, right? So that is there. And on similar lines, we have designed the issue unit, right? So issue unit is present at the output. So whenever one of the cores is done, so that issue unit is going to take that core's data and then send it to the next block. Again, this has the same 3 states, right? And again, this also synthesizes muxes near the in out underscore data, out underscore control and stuff. So when the processor is done, it says, so we indicated by a flag called done, right? So when depending on whichever processor is done, based on that we will give the control of the out underscore data, out underscore control interfaces to that particular core. So that is what is being done now. Let's look at the code for that, right? So we have built on the similar code. So our FSM core that we designed for the last lab, the FSM, that remains the same. That is the 5.4 along with the 4-threaded processor, right? So that code remains the same. So what we have done is we have added the code for dispatch unit here. So it's as I explained, it does the same processing. Like, I mean, it synthesizes a finite state machine, right? So I have wait, or the idle stage, where it's waiting. That means none of the processors are ready to take the packet, so that'll be an idle stage. Now whenever in underscore ready becomes high for one of the processors, that means it's ready, right? At that time I give the input interfaces control to the F0, that is the core 0, right? And then this is for the core 1, right? So that is what happens. A similar thing I've done for the issue unit. So this part of the code synthesizes the FSM for issue unit. So a similar kind of processing, except the interfaces are changed. And then I've instantiated this FSM0, and FSM0 and P0 are basically the entire block of pipeline along with the 5.4, right? Similar thing, FSM F1 followed by pipeline P1. That is the block of 5.4 and pipeline for the another part, right? So now that is the code that was written, and we have tested it both behaviorally and on netfpg, and it seems to work correctly. So my teammate is going to further explain the kind of processing we'll be doing for the packets, and also demonstrate the working of it in netfpg. Along with that, we'll also be demonstrating the snort using installing and running snort on the router, right?
Hello everyone, in this part I'm going to demonstrate how our assembly codes run on the 4-threaded pipeline. So for thread 0, it will change the IP address. If the source IP address is 10.1.0.3, it will change the source IP address to 10.1.4.3. And if its destination IP address is this one, it will change the destination IP address to this one. Also, for thread 0, it will calculate a new IP header checksum, so the IP header checksum will be changed. For thread 1, it does the same thing. If it is a UDP packet, it will add a number to the destination port. For thread 2, if it is a UDP packet, it will make the UDP checksum as 0. By doing that, the receiver of the UDP packet will ignore the checksum, so that it will not verify the checksum, so the UDP packet will not be dropped based on the bad checksum. And also, for if it is a UDP packet, and if the most significant bit of the register 28 is set as 1, this means that our hardware accelerator has detected a pattern of WW in the payload. So our software or our assembly code will change the payload from WW to FF. So for the third one, it's very similar as the second one, it's the second thread, but it will change the different word of the payload. So now I'm going to talk about how the IP header checksum is calculated. Based on the Wikipedia page here, the checksum field is the 16-bit ones complement of the ones complement sum of all the 16-bit words in the header. So let's take an example of the UDP packet we have actually captured. So in here, these are all the IP header till here. So let's go to here. This is the every actual IP header we captured, like here, right? So every line is a 16-bit word. So when adding all the 16-bit word except for the checksum, we can get the value from here. And this value has exceeded 16 bits, so the carry out will be added back to the 16 bit just like here. So this is this adding 1 will become this. And by doing the 1's complement, it will become this value. And this value in hexadecimal will be 6524. So it's the same as the UTP packet, IP header shown in here. Okay, so let's do the demonstration of the simulation of the four-threaded pipeline. So in our four-threaded pipeline, the source IP address is 10.1.0.3 and the destination IP address is 10.1.0.3. So in our IP header checksum calculation, because that the source IP address 10.1.0.3, it will be changed to 10.1.4.3, because that is the thread 0 will do like this. So by calculating the checksum, we know that it is 6123. So for the simulation part, this is the 6123 IP header checksum, and this is the IP source address 10.0.4.3, and destination IP address is 10.1.0.3. So the thread 0 works as we want. The checksum will be changed and the source IP address has been changed. And also for thread 2, we have added function like in here. If it is a UDP packet, the checksum will be set as 0. So in here, because this is a UDP packet, so the checksum here will be set as 0. And I think that's it.
Hello guys, welcome to the NetFPGA implementation of phase 2 of our project. So basically, we have implemented our design with the IDS design. So here we have used the same Detect 7B matcher from our previous IDS lab. So instead of the drop 5.4, we are sending the packets into our design, which is our dual core design. Basically, whenever the match is found, the matcher match will send a high signal with the in data and in control to the dual core design of ours, and we use the same hardware and software registers as the IDS Lab 7, so that we can use the same Perl script. Next, I will quickly show the demo of how everything works on the NetFPGA. So first, I will just reset everything and configure the nodes. After doing it, I will just load my bit file. So we can see that our bit file is successfully loaded. Next, I will start RKD. Oh, we have started RKD. So once again, we'll just go through how all of our threads work in both of our cores. So both the cores have the same functionality. We know that both of them parallelly process two packets simultaneously. So I will go through what the thread does once again. Already my teammates have explained that. So thread 0 will change if the source IP is coming from node N0, which is 10.1.0.3, it will change it to an IP address which is not there in the system, which is 10.1.4.3. Next, if a packet is destined to this non-existing machine, which is 10.1.4.3, it will be changed to 10.1.0.3, which will go to a machine which is there, which is node N0. So basically, I will show the functionality of how thread 0 works by pinging node N0. So when I ping node N0, we can see that we are pinging to 10.1.0.3, but the reply we are getting it from 10.1.4.3. So what have we done? Last time we did the same thing, but we were unable to get the ping back because of the bad checksums. Now this time we have dealt with the IP checksum and the UDP checksum too. But here we can see that us recalculating the checksum and editing not the payload, the whole packet is working. Next, what does thread through 2, 3, and 4 does? Thread 2, uh, if the packet is an UDP packet, and if it will change the destination port by adding 1000 hexadecimal to the destination port. And if we find a match, so it will basically, if there is a match, it will edit the payload. If there is no match, it will not edit the payload. First, let us check the basic functionality. Let us just set a pattern which is not there in our payload. So we can see that our pattern is successfully set. Okay. So then now I will demonstrate by running servers on node N1 and ping and hitting some data from node N2. Okay. So I will first SSH into N1. And I will SSH into N2 over here. So after SSHing into N1 and N2, I will first just run two servers, UDP servers on N1. One will be listening on port 8089 and one will be listening on port 12185. Okay. After doing that, I will just send one UDP packet. So we can see that this UDP packet was destined to 8089, but here it is being received at 12185 on node N1. So we can make sure that our second thread is editing the destination port. Next, since we set the pattern to AA, which is not there in the payload, we are not editing the payload in any way. Now I will set the pattern to WW. Okay. After doing that, I will just send the packet once again. We can see that the payload is edited. So the payload is edited, and we can see that we have done some kind of modification using thread 3 and thread 4, where the two threads will just change first word of the packet, and the thread 4 will change the second word of the packet payload. So basically both of them work on two different memory locations, which is thread 3 and thread 4. And finally, uh, after checking what pattern we got, the pattern, our IDS drop7b54 will send a high when it detects WW pattern, and that triggers our FSM machine, which will which will run its own process using the assembly code and change the payload. And after that, we will edit the payload, make all the checksums proper, and then we will send that packet to the destination. So we can confirm by this demonstration that our whole system works. And what are the improvements from the last lab? From the last lab, we were unable to hit the destination servers because of the bad checksums. We have dealt with all the checksums, and on top of it, we have disabled some checksums like the UDP checksum, because when the payload changes, the UDP checksum is for the payload 2. So basically, we have just set the UDP checksum to 0, and we have we set the UDP checksum to 0, and we send that packet, and that packet is successfully reaching the destination. I think from this, we can confirm that our whole design works. Thank you so much.
Hello everyone, in this part I'm going to show how to install Snort 2.0 and set some rules so that it can filter out some packets. For the Snort 2.0 installation, I follow this step. So basically, I download all the RPM files from here. So I think that these are the Snort binary files and others are the dependency files. So I follow this line to install the Snort. And after installation, it will look like this. So after installation, the Snort will be located in here. So it is like 2.9, version 2.9. And for the role setting, the role settings are located, or the configuration file of Snort is located in here. So in here we can set the configuration. We can open the configuration file, and for the configuration file, I have added two lines here. This is to set the DAQ module and set the mode as inline so that it can filter out packet. So now we can do the Snort. Also, let us talk about the local roles we have do for the Snort. So for the local rules here, I have set 3 rules. The first one is the ICMP. If this is the source IP address, this is the source port, and this is the destination IP address, and this is the destination port. So for every ICMP packet which has the destination IP address as this, it will set an alert. The Snort 2.0 will set an alert and print out this message. And for UTP packet that comes from, like, has a destination of home net here, it will drop the packet. And for also, like, it needs to match the content of these W. If it matches and this destination IP address matches this one, it will drop the packet. And if the contents matches this one, it will just alert. It will not drop the packet. So let me demonstrate it. So now we can do the Snort -T to we can do the Snort in this one. This is a Snort code, and the -Q means that's for quiet mode, and this is the log file, and for Q this is for inline mode, and this is the network interface. The two network interface we're going to use. I think this is corresponding to N0, and this is corresponding to N1, and this is the output. It will output to the console, and this is the configuration file we use. So now the Snort is running, and now I'm going to log into the N0 node, and this is the below is the N1 node. So in N0 node, I will set the iPerf servers in here, and in the N1 node, there's two data here. I'm going to send through iPerf. The first one is aaa.txt. It contains a lot of A here. And for another one is the www. It contains a lot of W here. So now I can do the iPerf in client mode and let's first send the AAA packet, the AAA date file. It is sent correctly to the server side, as shown in here and here. And in the Snort, it has detected that it has a pattern of AAA here, like in here, for the UTP packet. And let's send the WW text to the same from N1 to N0. Now, like, because of the www packet will be dropped, it will have the connection refuse here, and it does not send the packet correctly. So let's switch to the snore terminal. So all these packets are dropped here with the pattern www in here. And also we have another rules that is for pin, right? So in here, let's pin from N1 to N0. When doing the ping, when switching back to the snore, it will alert it because that ICMP packet is detected. And I think that's it. This is the part of the snore software demonstration.